वालेकुम सलाम व
वालेकुम सलाम।
रहमतुल्लाहि।
Bismillahirrahmanirrahim. Nahmadu wa nusalli ala rasulil kareem. So last week we started about the fluid dynamics, in which we considered the effect of energy. We discussed various types of energies, and finally we ended our lecture with this true kinetic energy and the derivation of this correction factor. So inshallah, from today we will first derive this Bernoulli's theorem. So do you know what is Bernoulli's theorem? Probably you have studied in your FSC and 10th metric class level. What is Bernoulli's theorem? Do you know what is Bernoulli's theorem?
Sir, pressure plus kinetic energy plus potential energy is equal to constant.
Okay, very good. Okay, so we will first derive this formula in Euler's form, and then we will discuss what is the difference between Euler's equation and Bernoulli's theorem. So now just refer to this figure. Let us consider a frictionless steady flow of an ideal fluid along a streamline. We shall consider the forces against acting in the direction of the streamline on a small element of the fluid in a stream tube. And after that, we will apply Newton's second law, that is F is equal to ma. So the cross-sectional area of the element at right angle to the streamline may have any shape and varies from A to A plus dA. So at this point, the area is A, and at the end of this fluid element, the area is A plus change in area. Okay, it can be positive or it can be negative depending upon the situation. So as we have considered frictionless steady flow, so in the chapter of fluid kinematics, we discussed about the steady flow, that the velocity does not vary at a point. Okay, I mean the velocity does not vary at a point, but it may vary with respect to the other point. So local acceleration means at a point the acceleration is 0, but it may vary with the position, that is convective acceleration with respect to some other point that is not 0. Okay, so pressure here there would be a pressure force. We know that pressure is equal to force per unit area, and if we want to find the pressure force, then we just multiply with the pressure. So small p represents the pressure. So at the bottom, the pressure force is PA, and at the top, the pressure is P plus dP, means pressure plus change in pressure times the area. Okay, P plus dP, A plus dA. The dimensions of this fluid element are its height, or you can say, if we consider like this, then this is ds and this is dz. And there is also a weight acting at the bottom of this fluid element, which is gamma A ds. This is the volume, and if you multiply with the gamma, then it becomes the weight. and it is actually acting down in downward direction. So if we consider forces in this streamline direction, then we need to take the weight component with respect to this theta. Okay, so this is all about its the figure. So as I said that we will apply a force is equal to ma. This is the Newton's second law. So first of all, we need to find the forces which are acting in this fluid element. And in the previous lecture, I talked about this fluid dynamics, in which we discussed various forms of equations, just like F is equal to ma is the main principle of finding the forces in fluid dynamics. And if we consider gravity force, pressure force, compressibility force, viscous force, etc., so the form of equation changes. The minimum number of parameters that are included in Newton's second law for Euler's equation are two, which was one pressure force and the other one was the weight force. So first of all, we will find this forces. Okay, F is equal to ma. So what are the forces involved in it? First of all, it is the pressure force. So A force acting at the top, so it is with the positive sign. Okay, this PA, and this the pressure which is acting from the top of the fluid element is P plus dP, D plus dA. Okay, so this is the second force. There's also a pressure which is acting from the sides of the fluid element, but we do not know the intensity of it. So what we do is we write it as pressure which is from the bottom plus P plus dP divided by 2. We just took the average of both the pressures. I mean, if we have this is P and this is P plus dP. So we just have considered the average of these two pressures, and if we multiply with the change in area, so it is basically the pressure which is acting over the change in area. So that's why we have included this. Okay. After that, if we do simplification, if we expand this equation just like PA, it is minus a PA minus PDA, etc. So these things will cancel and neglect this part. Okay, higher order terms. So when we neglect these higher order terms, then our final output would be minus dPA. Okay, so this is the pressure force. Next force is the weight component, weight force. Now, coming towards this side, weight is gamma A ds. So at in the figure, the final weight is written, which is gamma A ds with negative sign as it is acting downward. So if we consider its component, then it is basically gamma A plus half d. Again, it is the same. ये कैसे है भाई? ये इस तरह है A plus dA divided by 2. Okay, So here the area is A at the bottom, and at the top area is A plus dA. So we just took the average of this so that we have the area at the center. And when we simplified this thing, for cos theta, we write cos theta is equal to dz over ds. Okay, so just like this. So this, like, if this is theta and this is ds and this is dz. So from this figure we can actually find cos theta as dz over ds. So just replace cos theta as dz over ds, and after simplification our final output is gamma a dz. So these are the two forces, this particular part. So next thing is the mass of this fluid element. Okay. So we know that the mass of the fluid element is basically density is equal to mass per unit volume. So from this we can separate mass as density times volume. And this volume is the product of ds and dA, just similar to this one, gamma a dz. So in that mass it would be ds. Okay. So mass equal to rho v equal to rho ds, and we just take the average of area, a plus dA divided by 2. So it is rho ds a plus half dA and rho dsa. So ignore this half particular part, neglect. Okay, so the mass is rho dsa. So the last thing which is left in this equation is the expression A. How can we calculate this expression? Applying, after finding the mass, pressure, these are the forces F, apply a sum of the forces equal to MA along the streamline, we get these two forces equal to MA. So at the moment we haven't derived this A. So dividing by this volume dsa, just to simplify the equation, we just have divided this particular equation with dsa, and it simplifies the previous equation. It states that the pressure gradient along the streamline combined with the weight component in that direction causes the expression A of that element, recalling that A is equal to V dV by dt. अब area क्या होता है basically? Area is change in velocity with respect to time. So just multiply with you can say ds by ds. Okay, so it becomes dv by ds by dt, and we know that this ds by dt is basically velocity. So area becomes velocity times dv by ds. Okay, so just replace this area in this term as v dv by ds. And after that, just you need to simplify things, just like multiply this and rearranging. So this equation, change in pressure plus G dz plus P dV, it's actually we commonly refer to this equation as one-dimensional Euler's equation. Okay, so Euler's equation is for the equation of motion in which we consider only two forces: the force of gravity plus the force due to pressure. Similarly, if we add more forces in it, then the equation of motion would change from Euler's to say Navier-Stokes equation, Reynolds equation of motion, etc., etc. जी बेटा,
सर आपकी आवाज ठीक नहीं आ रही।
मेरी आवाज ठीक नहीं आ रही। आप अब इसमें मैं अब क्या कर सकता हूँ? बात सबको ठीक, बाकियों को आ रही है ठीक?
यस सर, हमें ठीक आ रही है।
तो मेरे बच्चे, आपके इंटरनेट में इशू में भी होगा। रिकॉर्डिंग हो रही है लेक्चर की, तो यू कैन download it and you can listen to that recording. Okay. So this equation is actually Euler's equation is applies to both compressible and incompressible flow. Since the variation of P over the element length ds is small, means the change of pressure over the element length of ds is small. Now, for compressible fluid, actually we do not, being a hydraulic engineer, we consider our fluid as incompressible. Okay, so for compressible flows, if we want to transform this Euler's equation for compressible flows, then we need to do some more derivation and procedure, and the final output will be different. Okay, but we will not derive this for compressible flow. So we would only consider an incompressible flow. Okay, for the case of incompressible fluid, gamma is constant. Okay, so we can integrate equation just like our final equation of Euler's equation was dP over gamma plus dz plus dV square over 2g. If we integrate this equation, we can actually replace this g. Actually, our final Euler's equation was dP over rho plus g dz plus v dv. Take the integration. So it becomes P over rho plus gz plus v square over 2. It is constant. And if you further simplify this, divide whole terms by g. So this will cancel. So this becomes gamma. So our final result is P over gamma plus z plus v square over 2g is equal to constant. So this is our final Euler's equation for incompressible flows. Incompressible fluid. Energy per unit weight. Okay, so we know this famous equation as Bernoulli's theorem. Okay, so an equation, Euler's equation for incompressible flow is basically the Bernoulli's theorem, and आगे इसकी scientist की detail है, and if you multiply each term by first by g and then below, then we obtain alternate forms. We can also relate this equation in terms of unit mass and unit volume as well. Okay, so now what are the assumptions of this Bernoulli's theorem? It assumes that the fluid is flow is frictionless. It assumes viscous friction effect are negligible. It assumes that the flow is steady, means the velocity at a particular point or local acceleration is zero. It assumes the fluid to be incompressible. It assumes no energy is added to or removed from the fluid along the streamline. So during the path, there would be no losses actually. Okay, so these are the some assumptions of Bernoulli's theorem, and I believe it is very simple. Okay, so we will solve one problem. Any question? कोई question किसी का? Okay, so a glycerine fluid having a specific gravity of 1.26 in a processing plant flows in a pipe at a rate of 700 liters per second. So discharge is given, which is Q. At a point where pipe diameter is 600 millimeter, the pressure is 300 kilopascal. So this is point 1. So this is the dia, say D1, and this is pressure P1, which is 300 kilopascal. Find the pressure at the second point where the pipe diameter is 300 millimeter. So D2 is also given, and we need to find P2. And the elevation difference between these 2 points is 1 meter. So this is actually Z. Basic. We need to consider some datum point. So this is our datum. So Z1 would be 0 and Z2 would be -1 as we are moving downward from the datum. Okay, so you need to apply Bernoulli's theorem, which is P over gamma, P1 over gamma plus Z1 plus V1 square over 2G is equal to P2 over gamma plus Z2 plus V2 square over 2G. So this is the equilibrium equation. You just put all the values here. So you have P1, but you do not have P2, which is actually you need to find. Z1 is 0, Z2 is -1. Velocity V1 कैसे आएगी? You have the discharge Q, and from this diameter A1 you can find area. Okay, and similarly from D2 you can find A2. So by using the continuity equation Q is equal to AV, Q is equal to AV, you can find V1 and V2. Okay, discharge remains the same. So once you have all the components of velocities, then you just put in this equation and you will find this pressure. Okay, solution is given. The gamma value is constant for on both the sides. You can find V1, V2 as this one, or you can separately find V2 similar to this equation by just dividing with the Q. Q is equal, Q by area. Okay, so from this you can find this pressure. Any question? Any question? Because this will end this lecture. Actually, it was a part of previous lecture, लेकिन हम खत्म नहीं कर पाए. So okay. This is your assignment 2. I will upload this on Microsoft Teams in Word form. So you can download from that thing, from that file, and the time limit is 2 weeks. Any question? So why the number of participants are very less? Only 57. Okay, so we are going to start our next lecture, which is lecture 7. In this lecture, it has 2 parts. The first part is related to previous lecture, or it is the continuation of previous lecture, in which we will study about energy conservation for real fluid. Okay, so previous derivation of Bernoulli's theorem was for ideal fluid in which there were no losses, but this energy consideration here is for real fluid. Okay, and you know that in real fluid there are certain losses due to friction of pipe, and losses due to, say, if the pipe is turning, or then it has some loss at this point, and if a pipe has a bend, or it has a fall here as well, then there would be some loss of energy in it. And similarly, if we have certain expansion or contraction of pipe, then at these points there would be some losses. So yes, in real fluid there are losses, and we need to separately include the effect of losses in Bernoulli's theorem. Okay, so equation for steady motion of a real fluid along streamline. The derivation is all same. You can see that the pressure, force, change in pressure, weight, etc., all same, except one thing. As this is a real fluid, so there would be um, an effect of fluid friction. Okay, so it is represented with tau here, friction. Okay, so this tau is an additional term which will be included in this particular part. And the formula for this tau, this shear stress, shear force is tau shear stress times pressure. Okay, not pressure, this is basically area. Tau is equal to force per unit area, and this force is equal to tau times area. This is shear stress. So area इसमें क्या है जी? क्योंकि इसमें अब हमारे पास एरिया shear stress सर्कमफ्रेंस पे लग रही है. shear stress जो है वो पाइप की वॉल्स, पाइप की बाउंड्रीज पे लगती है, वॉल बाउंड्रीज पर. So we need to consider its circumference area, perimeter times ds. The P is the perimeter, okay? P being the perimeter of the end area A. Similarly, just like if it has perimeter P at the bottom and it has perimeter P plus dP at the top, then we can find the average perimeter as P plus dP and P plus, okay, and divide it by 2, then you can have this one. So the only thing which we need to include in our previous derivation is this frictional force. As you can see, this force equal to MA, this is the pressure force, this is the weight force, and this is basically the shear force. Okay, I will not derive this equation because it is same thing. The only thing is an addition of this shear force. So finally, if you if you find the energy per unit weight, then you can see that this is an additional term. This is constant. So this is at section 1 and this is at section 2. The additional term is tau PL over gamma A. Okay, so this is an additional term which is tau PL over gamma A, which is the shear force. Yes. So steady flow incompressible assumptions are same as that of the previous one for ideal fluid. No energy added or removed. Okay, so what is basically the head? If we compare equation 5.12, this one, with the previous lecture equation, Bernoulli's theorem, which is 5.7, which was for ideal flow, we can see the only difference is the additional term tau PL over gamma A. The only difference is the additional term tau PL over gamma A, which represents the loss of energy per unit weight due to fluid friction between points 1 and 2. Okay, अब इसका मतलब क्या है basically? For example, ये probably मैंने पहले भी explain किया है. Say if we have a glass and if we roll this ball, एक हमने इस पर force लगाई, so probably it will come somewhat here after some time. Okay. Similarly, if we have a very rough material of iron, the ball is having the same mass and same force is applied to roll this ball. So what do you think, that will it cover more distance than glass or less distance?
Less distance.
Less distance, very good. So the ball will finally reach somewhat here. So this difference between for ideal condition having no friction, so this is an ideal condition, and in this we do not consider friction. Okay, but for real fluid there would be some friction, and due to that friction there would be a reduction in energy. There would be a reduction in energy loss of, basically it is the loss of energy per unit weight due to the fluid friction between points 1 and 2. So this is point 1 and this is 2. So this is the basically head loss due to friction. Okay, this particular part.
Excuse me, sir.
जी बच्चे.
सर ये रो PL और gamma A में L क्या है?
L length of pipe है. जितनी डायमेंशन उसकी आएगी ना, से इसमें यहाँ की जब हम डिराइव करेंगे, जस्ट वेट. This is the distance between them is L. After integrating from some point 1 to point 2 on same stream where the distance between, तो जो वहाँ पर ds था उसको फिर हमने L से रिप्लेस कर लिया. फॉर एग्जांपल dz को हम इंटीग्रेशन के बाद z ले लेते हैं, तो सिमिलरली ds को हमने जब इंटीग्रेट किया तो इट बिकम्स L. ओके, ठीक है?
Okay, sir. Yes, sir.
Okay. So this is the head loss basically. Head loss का नाम आप काफी आगे सुनेंगे. Head loss due to friction, head loss due to other things. So in actually fluid in a pipe, there are two types of losses. One we consider as a major loss, and the other losses we consider in minor losses. ठीक है? In major loss, the loss is due to friction. Just like this one we have discussed so far. Whereas all the other losses, for example, sudden turning, sudden fall in a pipe elevation, sudden expansion, contraction, etc. So all these losses come under the minor losses. Minor head loss, major head loss. So the loss due to friction is very large as compared to other small losses. Therefore, we consider it as a major loss. Okay. So the dimensions of this energy loss terms are length only, which agrees with the all other terms in question. So this term is the form of head, just like head P over gamma we considered in very initial lectures. So wall friction head loss. The friction causing this loss of energy occurs over the boundary or surface of the element of area PL. Okay, perimeter times length. So this is safe length and it is perimeter P. Area would be PL. Capital P denotes perimeter, small p denotes pressure. When as occur, often we consider the stream tube to fill the conduit pipe or duct conveying the fluid. PL becomes the inside surface area of the conduit wall and tau becomes the shear stress at the wall tau naught. Okay. The tau naught जहां भी आएगा वो आपने क्या करना है, shear stress at the wall. ठीक है, इस वॉल पे जो भी shear stress होगी वो tau naught है, and shear stress at some distance away from the wall at say x, it represents with tau. So tau is a general shear stress and it is used to represent the variation of shear stress within the pipe at any distance away from the wall, whereas particularly the shear stress at the wall would be represented as tau naught. Okay. So the wall friction head loss, it becomes tau P. It is the same thing. This tau P L over gamma A. So this HF is tau P L over gamma A. So just you can replace tau P L over our gamma A in the previous equation here. This one 512. So this is basically the head loss HF due to friction. F represents friction. Okay, so this is head loss due to friction. And if we have some other losses, okay, why we have subtracted this from the first term? Okay, why we have subtracted this? Actually, in this figure, if you see that at one point, or you can see that this loss, the first point due to an ideal fluid, it has some extra thing. So we subtracted the head loss from that first part. Okay. Or you can also write it as, instead of this, you add HF here. Means that this is the amount of head loss which the second point measures less. Okay. So we have added this head loss at point 2. Either we can subtract from point 1 or we can add from point 2, initial final. Okay, so if we have minor losses as well, then this equation would become, say, minus HF, which is friction, minus HM. And HM will include many losses. So in detail, you will study about these minor losses in fluid mechanics too, when you will study about the pipe flow, phenomena, pipe flow mechanics in detail. So at the moment, it is this knowledge is sufficient about the head loss, which is due to friction only, friction plus minor losses. So as in most common, the conduit is of circular pipe of diameter d. So we can replace P by A here. This P by A, which is the perimeter times our area. We know that if any circular pipe is having diameter, then we can actually transform this formula in terms of diameter directly. Instead of area, if we know the diameter, then we just transform, we can just write this formula of HS in terms of diameter. So we know P is pi d and area is pi d square by 4. So the previous equation becomes 5.15, which is 4 tau naught L over pi d. So fluid friction loss from any such cause, including wall or pipe friction, we commonly refer to as head loss, denoted by HL. So wall friction head loss is usually a part of, but it may be all of the total head loss in a given conduit, then HL is greater than HF. बात समझ आइए, HL is the total head loss, and it would be a summation of HF plus HM. At the moment, if we are not considering this minor losses, say it is equal to 0, then HF would become equal to HF. Okay. However, in most of the cases, this total head loss would be greater than this HF. How as HL is equal to HF plus HM. So in that case, this total head loss would be larger than the frictional head loss. Any question? Any question? कोई क्वेश्चन नहीं है. So water flows through a 150 feet long 9-inch diameter pipe at 3.8 Q6. Water flows through a 150. अभी length given है, dia भी given है pipe का, ठीक है? और discharge भी given है, which is 3.8 Q6. At the entry point, the pressure is 30 psi. So this is pressure 1 P1. And at the exit point, which is 15 feet higher than that of entry point, the pressure is 20. This is P2. So Z1 here would be 0 and Z2 would be plus 15. The difference in elevation. Between these 2 points, find the pipe friction head loss, the wall shear stress tau naught, and the frictional force on the pipe, F. Pipe friction head loss, HF. So how can we proceed? How can we do it? जी बच्चों बताएंगे. लेकिन डायमीटर दोनों का सेम है, इस पॉइंट पे भी इस पॉइंट पे भी. सो V1 स्क्वायर ओवर 2G and V2 स्क्वायर ओवर 2G, इट विल बी सेम. एग्री करते हैं? क्योंकि Q से हम जब दोनों का निकालेंगे बोथ विल बी सेम, so we can simply cancel. So our equation is P1 over gamma plus Z1 plus V1 square over 2G minus HF L is equal to P2 over gamma plus Z2 plus V2 square over 2G. So we have this pressure. P1 is also given, P2 is also given. Okay, Z1 0 है, Z2 minus plus 15 है, ये दोनों भी given है. ये कैंसिल कर दें या इसको अलग से लिख लें, तो जब आप इसको सॉल्व करेंगे, so you will get the value of HF, which is the pipe friction head loss. पहला पार्ट हो गया. So after that, you just write the formula of HF, which is tau naught PL over gamma A. Tau naught PL over gamma A. पहला पार्ट हम यहां से आएंगे, ये पार्ट हमने कर लिया. प्रेशर ये 144 इसलिए लिखे पाउंड्स पर स्क्वायर इंच है, तो उसको फीट में कन्वर्ट करने के लिए 12 क्रॉस 12 किया, इट इक्वल्स टू 144 एज द प्रेशर इज गिवन इन psi, which is pounds per inch square. So we need to transform to pounds per foot square, so that's why we multiply with the 144 here. यहां तक किसी को ना समझ आई हो पार्ट ए? पार्ट ए की किसी को ना समझ आई हो? Okay, so pipe friction head loss के हमारे पास से एक क्वेश्चन है, which is HF4 in terms of diameter, 4 tau naught L over pi gamma d. तो वहां से tau naught को आप सेपरेट कर लें. This is basically tau naught, okay, from equation 5.15. tau naught को हमने सेपरेट किया तो क्या आ गया? HF gamma d divided by 4L. HF gamma d divided by 4L. So after solving this thing, then you will be able to find this tau naught. Okay. So the third thing which we need to find is friction force of the pipe, F. And we know that this shear force, tau naught is equal to force per unit area. And if you want to find frictional force, F is equal to tau naught times area. And here area is PL. Okay, so tau naught times PL. P is gamma d, again this is P. And after that you will be able to find this frictional force. So three things. The only thing which you need to find is HF, and after that just write this HF in the formula of shear stress. And once you have shear stress, just multiply with the area to get the force. Any question? Any question?
सर 144 का दोबारा बता दें.
144 बच्चे प्रेशर इसमें 30 psi. psi क्या होती है? पाउंड्स पर इंच स्क्वायर. ओके, आप देखिए यूनिट्स एक रखेंगे ना, या तो आप से फिट रखेंगे या इंच रखेंगे. सो इट्स बेटर टू यूज दी हायर यूनिट्स. फॉर एग्जांपल फिट है या इवन मीटर्स है, तो जितनी भी आपकी सेंटीमीटर या मिलीमीटर है उसको आप ट्रांसफॉर्म कर देंगे मीटर्स में, यूनिट कन्वर्जन. Similarly, in this state, we will follow the fit CFS Q6 fit cube per second. ठीक है. So diameter को भी आपने fit में change करना है 9 divided by 12 करके. Similarly, 30 psi है. It is 30 pounds per inch square. So inch, एक इंच में कितने ये वो होते हैं fit? 1 by 12. तो मीन्स अगर इसको 1 by 12 करूंगा, इंच स्क्वायर है ना, तो 1 by 12 times 12, तो ये बेसिकली 30 से फिर मल्टीप्लाई हो जाएंगे, क्योंकि डिनोमिनेटर में भी ये डिवाइड हो रहा है. ठीक हो गया?
यस
तो 12 क्रॉस 12 144 आ गया.
ओके सर.
ओके, एनी अदर क्वेश्चन? So these are some more problems which are a part of your assignment. Solve it by yourself. I mean, it is just like this one, this problem. If you have understood this problem, then you will be able to do these problems. At least you must read. If you feel any confusion, then in the next week you can ask for a hint basically, but I will not tell you the exact solution. Okay, so this whole terminology, we call it as a head. Okay, P over gamma plus Z1 plus V, and this is head loss minus HL. So in above equation, each term has the dimensions of length. Thus, P over gamma, called the pressure head, represents the energy per unit weight stored in a fluid by virtue of its pressure under which the fluid exists. Z, called the elevation head or potential head. V square over 2G, called the velocity head. Okay, so these three heads, the sum of these three terms known as total head, which is represented with H. So wherever term H is written, then it is basically a summation of pressure plus elevation plus velocity head. So now coming towards the practical applications of this Bernoulli's theorem, that and practically where this principle is actually applied. So we will discuss three of its applications. One is the Venturi meter, orifice meter, and Pitot tube. So Bernoulli's theorem or equation, Bernoulli's equation, is a basic equation which has the widest application in hydraulics. Okay, since this is applied for derivation of many formulas, therefore its clear understanding is very essential. I mean, ये आगे भी derive करने के लिए भी इस्तेमाल होती है this equation. So some of its application which we are going to study in this lecture is Venturi meter, orifice meter, Pitot tube. So first part is the Venturi meter. A Venturi meter is a device for measuring discharge in a pipe. For example, if we have a very long pipe and if we want to measure, say, the discharge in that pipe, and if we want to do continuous measurement means अगर एक से गैस पाइप में से गैस भी जा रही है तो आपने continuous measurement आप रिकॉर्ड देख रहे हैं कि सुबह इस पाइप में कितनी गैस रन कर रही है, इवन पानी भी कितना पानी चल रहा है, कितना पानी कम है. सो आप क्या करेंगे, उस पाइप का सेक्शन से इफ यू हैव अ लॉन्ग पाइप, मैंने यहाँ से एक पाइप को रिमूव किया और उस जगह पे मैंने वेंचुरी मीटर फिक्स कर दिया. वो कुछ इस तरह का होगा, यानी कि इस जगह पे, like this one. So this is the continuation of pipe, and I fix this Venturi meter here. So the Venturi meter is a device for measuring discharge in a pipe. It has three parts. Convergent cone. The first part is the convergent cone in which the diameter of the pipe actually reduces, and after that this straight line is the throat, and the final part, the third part, at which the divergent cone means the diameter of the pipe is diverging, it is increasing. Convergent cone, throat, and divergent cone. So these are the three parts for this Venturi meter. And by measuring the difference between the heads at pipe and in this throat, we are able to find the discharge. Okay, just like this is the practical picture. So this is, say, some gas pipeline. Okay, and in this pipeline we just fix this Venturi meter, and it has some digital measuring device. So from this reading we are actually able to find out that how much gas or say water is passing in this pipe. The discharge may vary, as if the velocity of water is very less, then obviously the area, keeping the area constant, the discharge would be less. Okay, so so the amount of discharge can be measured with respect to this Venturi meter. So now we will discuss about its three components. One is the convergent cone. Converge means the converge or your diameter is converging. So it is a short pipe which converges from a diameter D1, which is a diameter of pipe in which ventimeter is fitted. Okay, this D1 is the diameter of the pipe. Converges come over from D1 to smaller diameter D2. The convergent cone is also known as inlet of the ventimeter. The slope of the convergent sides is between 1 in 4 or 1 in 5. So this is about the convergent cone. The slope of the convergent sides is between 1 in 4 or 1 in 5. So the next part is the throat. So this is the convergent part, and after that, where the diameter is, say, remains the same at some length, it is a small portion of circular pipe in which the diameter remains, in which diameter D2 is kept constant. It is a small portion of circular pipe in which the diameter D2 is kept constant. So this is the throat, this one. This one. And finally, we have the divergent section, which is diverging. It's a pipe which diverges from a diameter D2 to a larger diameter D1. Again, say this is the D1 is the diameter of the pipe. So the last part of this ventimeter is the divergent cone, in which the diameter of diverges to its original pipe diameter. Okay. So what do you think, that there would be a change in pressure or not in this ventimeter? जी बच्चों, would there be a change in pressure or not? Okay, chalo, next question आपसे.
No, sir.
It's written the length of the divergent cone is about 3 to 4 times that of convergent cone. Why the length of the divergent cone is about 3 to 4 times that of convergent cone? Why the length of convergent and divergent is same? Why it is, why it is not the same? नहीं पता. How it operates? It consists of a rapidly converging section which increases the velocity of the flow and hence reduces the pressure. ठीक है? According to Bernoulli's law. Bernoulli's law क्या कहता है जी? P plus, ये पढ़ा हुआ आपने, half rho V square is constant. So if we have pressure and velocity are inversely proportional to each other. If pressure increases, according to this law, the velocity decreases to keep the algebraic sum constant. Okay, so this is constant. So to keep the algebraic sum constant, if pressure increases, then velocity will be reduced. So in a convergent section, it actually reduces the velocity. Sorry, it increases the velocity as the area is reduced against a constant discharge. Therefore, the pressure would be reduced. It then returns to its acceleration between section 1 and 2. It's written. अब आ जाएं जी सेकंड सेक्शन पे, between 2 and 3. अब हमने क्या किया? It then returns to its original dimensions of the pipe by gently diverging diffuser section. Now the velocity will be reduced. So therefore, according to Bernoulli's law, the pressure will increase. Okay, pressure अब second section pressure बहुत ज़्यादा बढ़ रहा है. By measuring the pressure difference, the discharge can be calculated. अब इसके लिए कोई formula हम derive करेंगे कि how can a discharge be calculated by just measuring the pressure difference. So this is particularly accurate method of flow as energy losses are very small. अब next आगे जी why the divergent cone is made longer. As अब इसका simple answer तो ये है क्योंकि pressure जो है वो बढ़ रहा है और एकदम sudden change in if we increase the pressure suddenly, then there are chances that the pipe walls may break or there would be a bursting of pipe will happen. Okay, so as a result of retardation, the velocity decreases and pressure increases. So if the pressure is rapidly recovered, then there is every possibility for the stream of liquid to break away from the walls of the meter. In order to avoid the tendency of breaking away the stream of liquid, the divergent cone is made sufficient longer. Okay, the divergent cone is made sufficiently longer. Another reason is to minimize frictional losses. The divergent cone is 3 to 4 times longer than convergent cone. So this is the reason that why the divergent cone is a bit longer than that of a convergent cone. It is actually to compensate the change in pressure, or you can say the allow the pressure to increase slowly. I mean, it's to and it is to avoid sudden increase of pressure. Any question? Just like this one, velocity is low, cross-section area is high, and there would be high pressure. And if velocity is high, cross-section is low, there will be low pressure. So rate of the flow must be constant at all points along the pipe. It's the velocities that change. Q same रहेगा. So now moving towards the derivation of the formula for measurement of discharge. That how can we measure the discharge? It is the principle is same as that of manometer. You remember manometer? You remember manometer in which the mercury was the fluid.
Yes, sir.
So consider a venturimeter through which some liquid is flowing. Let it has two parts. One is having in a pipe section at one, and one is having in a throat section. So this is throat and this is pipe. So one is the section one is at pipe and section two is at throat. So P1 is the pressure at section 1, V1 is the velocity of water at section 1, Z1 datum head at section 1, similarly area A1 area venturimeter at section 1, and corresponding values are 2 at section 2, P2, V2, Z2 and A2. So applying Bernoulli's equation at section 1 and 2, very simple. P1 over gamma plus Z1 plus V1 square 2G is equal to this thing. Since the datum line of the axis is venturimeter is same है, datum and same है, तो Z1 is equal to Z2. Z1, Z2 दोनों same है तो वो cancel हो जाएंगे. P1 over gamma plus V1 square 2G is equal to this. इसको इधर ले, इसको इधर ले जाए. ये इस तरह बन गई question. Okay. Now according to continuity equation, Q is equal to A1 V1 is equal to A2 V2. So can we write V1 like this? लिख सकते हैं ना? ये वापस V1 को हमने इस इक्वेशन में पुट कर दिया. And after solution, just take the common V squared 2G. So P1 over gamma minus P2 over gamma is this one. So we know that this P1 over gamma minus P2 over gamma is the difference between the pressure heads at section 2 P1 H is equal to P1 P is equal to gamma H होता है ना, तो H क्या होता है P over gamma, यही है. So this P1 over gamma minus P2 over gamma is the difference between the pressure heads at section 1 and 2. So when the pipe is horizontal, this difference represents a venturi head and is noted by H. Okay, अगर तो pipe horizontal है, means Z1 and Z2 are same, then this P1 over gamma इसको हम H से represent कर सकते हैं. Otherwise, it would be P1 over gamma अगर से venturi meter इस तरह inclined है, Z1 और Z2 different है, तो P1 over gamma plus Z1 minus P2 over gamma plus Z2, it would be equal to H. Okay, ये याद रखना है. अगर तो Z की वैल्यू सेम नहीं है तो इस H में P1 और gamma plus Z1 भी आएगा और Z2. So from this we can find this velocity V2 2gh and this one, and calculations give discharge according to this formula. The discharge is under ideal condition and is called the theoretical discharge. Actual discharge is less basically. Therefore, we need to multiply with some coefficient C, coefficient of venturi meter, and the value of C is always less than 1. Okay, so value of C is always less than 1. So ये V का फार्मूला है, तो आप Q अगर निकालेंगे तो कर देंगे, तो you can have this formula of Q. So where CD is the coefficient of venturi meter and its value is less than 1. Okay, and एक और चीज अब इसमें important है. The venturi head H in the above equation is in terms of liquid head, but in actual practice this head is given as mercury head. In such case, the mercury head should be converted to liquid head. Just like हमने पिछले पढ़ा था जब हम fluid statics पढ़ रहे थे कि अभी हमने जो fluid इसमें कोई भी हो सकता है, वो पानी भी हो सकता है, वो गैस भी हो सकती है, लेकिन जो हम हेड मेजर कर रहे हैं वो मैनोमीटर में मर्करी है, तो मर्करी के हेड को हमने ट्रांसफॉर्म करना है फ्लूइड के हेड में. ठीक है, तो ये वही फार्मूला जो हमने पहले ऑलरेडी पढ़ा था. ठीक है जी. Similarly, we can have an inclined manometer, venturi meter as well. अब inclined होगा तो फिर ये Z1 इसमें ऐड हो गया. So पहला प्रॉब्लम करते हैं. स्टेटमेंट पढ़ें. A venturi meter with 150 millimeter diameter, so D1 is 150 millimeter and is equal to 0.15 meters. D2 at the inlet and 100 millimeter at the throat, so D2 क्या हो जाएगा 100 millimeter और 0.10 meter. At throat is laid with axis horizontal axis है Z1 Z2 same हो जाएंगे and is used for measuring the flow of an oil having specific gravity 0.9 हो गया जी oil की. The oil mercury differential manometer shows oil mercury shows a gauge difference of 200 millimeter. ठीक है जी, गेज डिफरेंस 200 मिलीमीटर है. तो ये फार्मूला में अगर हम देखें, ये x जो लिखा है यहाँ पे, so here this is basically x. Coefficient CD जो है that is given which is 0.98. Calculate discharge. Q find करना है in liters पर मिनट। ठीक है जी। फॉर्मूला क्या है Q का? Q का फॉर्मूला है जी Q इज इक्वल टू C A1 A2 A1 स्क्वायर माइनस A2 स्क्वायर अंडर रूट 2GH। ओके, अब H हमने इसमें A D1 है D2 है, उससे A1 A2 आ जाएगा पाई D1 स्क्वायर बाय 4 करके। ठीक है जी। और H का फॉर्मूला है जी X टाइम्स SH डिवाइड बाय S नॉट माइनस 1 और 0.2। अब इसको इसका एलसीएम वो ले लें, एलसीएम ले लें, सो 13.6 माइनस 0.9 डिवाइड बाय 0.9, सो H के आगे जी 2.82 मीटर्स ऑफ ऑयल। वंस यू हैव H, एरिया भी कैलकुलेट कर लें, सारी चीजें इस पर डालें Q के अंदर, सो यू विल हैव Q इज इक्वल टू 63.9 लीटर्स पर सेकेंड। ओके, और आप उसको 60 से मल्टीप्लाई करके 3834, आंसर मैं आपको बता रहा हूं। फाइनल आंसर Q का क्या है? 63.9 टाइम्स 10⁻³ मीटर क्यूब पर सेकेंड। इसको आप कन्वर्ट कर लें 63.9 लीटर्स पर सेकेंड। 60 से मल्टीप्लाई करेंगे 63.9 टाइम्स 60 इक्वल टू 3834 liters per minute. Okay. So inshallah today we will conclude this lecture a bit early because I have a meeting. So that's why मैंने lecture भी आज जल्दी रखा है. So inshallah if you have any question then you can ask in the next class. Okay.